I have made you co-host 3:30 so that you can take the recording. Okay. So we have started our discussion based on fault analysis for three-phase in terms of balanced or unbalanced scenario. Like unbalanced scenario, it might be single line to ground fault, double line to ground fault, or line to line fault. Okay, there might be different possibility there. Actually, we have started the discussion for fault in terms of single line to ground that I can recall or review at the beginning so that you can get that idea once. Okay. Okay, single line to ground fault. Actually, what you have to do when you have sequence component, okay, or symmetrical sequence unsymmetrical phasor. What you have to do for that phasor? It might be voltage phasor, it might be current phasor, right? Or it might be impedance, which is unsymmetrical. And if you have that unsymmetrical phasor, you need to determine its sequence component, which is positive, negative, and 0. That is denoted by 1, 2, and 0 respectively, right? So that is for individual quantity like voltage or current or impedance. Okay, this class is very important for you regarding those concept in the circuit level. Okay, so be careful and attentive regarding today's lecture because it is covering one very important topics regarding fault analysis for three-phase in terms of sequence component or sequence network, because it is in terms of circuit, so we can say sequence network. Okay, so sequence network, it might have single line to ground fault first of all. So to ask if you cannot understand that part, okay, because this class will be important session for you. So if you have any problem regarding understanding, you need to ask that part. Otherwise, you may miss the opportunity to learn. Okay, first part is the single line to ground fault case. Actually, when do we consider that scenario, or what will be the outcome if we have single line to ground fault? Three different aspects you have to address. One is when you have the fault scenario, okay, that fault will have some voltage case, right? Based on the fault impedance, initially you have the open circuit, but when you have fault, it will generate some path, and that path will flow some fault current through that fault impedance. Okay, in that case, you will have some voltage drop over that phase A terminal, and for phase A and B, you will have 0. So what you have to do using that concept of voltage and current, you have to generate your ABC sequence. Okay, ABC sequence in terms of, first of all, you have to generate 0, 1, 2 sequence, then you can shift that to its equivalent ABC sequence. Here you can see IB, IC is already 0 due to single line to ground fault. This condition actually depend upon the fault category. Okay, if it is another types of fault, the equation for that fault will be different. Okay, let's see another scenario, line to line fault. Here you can see what will be the case when you have line to line fault. Your fault impedance will be in between two lines. Okay, and there you have the issue of that current flow between that two lines. Actually, IB plus IC, what will be that? Equals 0, right? When you have double line fault, is it clear? IB plus IC equals 0 for double line fault.
স্যার বুঝিনি স্যার এটা কেন
Sir, this
বলছেন?
part, sir.
বুঝতে
Could you
পারছো?
repeat, sir?
বোঝো নাই?
Repeat, sir.
আচ্ছা
Kindly, sir. Yes.
আচ্ছা দেখো, you have to check that diagram first. Okay, if you have double line to ground fault, what will happen? You will have short path between them, right? And that will be the, in terms of fault impedance, which is ZF. So you have short path between them. That means IB is there, flowing IC is there. What will happen? They will make a combined path, right? Or common path. And their direction is different. That means IB plus IC, they will cancel each other in terms of that fault path, right?
Oh,
That's why fault current for double line scenario will be IB plus IC with 0. Okay,
Sir,
IB
will
plus
they cancel
IC,
each other for unbalanced load too?
unbalanced load, not unbalanced because of double line fault. Double line fault, okay? That means you have short between two lines. This is the line to line fault case. And that will certainly create unbalanced, okay? Because you have fault there and it is not faulty path. So that will generate certainly IA, IB, IC unbalanced scenario. Okay, and that unbalanced scenario can be determined based on that equation. That means if we just want to consider ABC and 0, 1, 2 domain, what will happen? In this side, you have the ABC information. This is IA, okay, IB and IC. So if we just think of, yes,
Sir, could you kindly, sir, repeat the single line to ground fault again that we were discussing that day, sir? So,
Sir,
single line, okay. I am just trying to compare those two scenarios so that it will be easier for you. Where you have to think differently. Okay. I will show
Sir.
that also. Just
Sir.
yes. Is there any question?
You are going so
Yes.
fast. Can you somehow slow down, please? I mean, can you somehow
Okay.
slow down? Okay. Yeah.
Okay. Actually, okay. So you have to be careful what I am discussing now. Regarding 0, 1, 2 domain, okay, if you want to find ABC or 0, 1, 2 domain interrelation, this equation is already known to you, right?
Yes.
How can we interrelate ABC and 0, 1, 2? IA 0, 1, 2 is equals to A inverse I ABC, right? This part is ABC.
Yes, sir. Yes.
And this ABC, how we can place there? First term is I. You don't have any connection for that, right? Only short for second and third phase. Okay, second and third phase has the short connection, but this is open. That's why you don't have any current. So IA will be 0 first term. Second term IB, it is normal IB. How can we place IC? This can be put based on that fault condition. Okay, IB plus IC equals 0 due to double line fault. And that case, this IC will be minus IB, right? So
Yes.
these are the scenario to place this different current. Now we can check the earlier class lecture, how we can put their information there. If it is another types of fault, which is single line to ground, what will happen? Single line to ground case, only IF current will be there. IB and IC will not be there, right? Because you have only fault path through that phase. So
Yes,
current will only be at first phase. So first phase will have IA
Okay, sir.
and IB and IC will be 0 for single line to ground scenario. They are same, right? This part you have to be careful. Okay, how we can put the information for this part? Now we can compare double line to ground fault. For that case, what will be the scenario? Double line to ground fault. This is the double line to ground fault scenario. When we have double line connected short and we have the fault. Okay, so how can we generate or make the equation? IB, for that case, what will be the condition? actually we have IB and IC in terms of fault impedance. For that, okay. The drop over VB VC will be ZF IB plus IC, right? The voltage drop over that fault impedance for that path will be ZF IB plus IC. So IA for this case will be only IA dot IA0, IA1, IA2, which is 0 because you don't have any current for that. Likewise, the double line fault case, IA will be 0. Actually, what you have to do, you have to use IA first in terms of ABC first step. Then you can generate 0, 1, 2 from that IABC. Okay. And after that IABC determination in terms of 0, 1, 2, you have to put that information for voltage. Here you can see when we put the single line to ground for that was discussed in last class. It is the matrix outcome, right? The simple multiplication will generate this expression, single line to ground fault expression. Okay, when we have only IA present, which types of fault this one? If we just check this matrix, can we identify which types of fault this one should be?
Yes, sir. Double line, sir.
It's a single line.
No,
Ground.
it is
Single
single
line.
line.
Oh, sorry, sir. Single
Single
line.
line to
My bad.
ground.
Yes, sir. Yes.
Single line to ground. Okay. If it is double line, in that case, there will be some minus sign because
Yes.
they will be resultant. So
Yes.
it is actually single line to ground. So single line to ground fault matrix will generate the expression like this. We know how to find that, right? Just simply matrix multiplication will give us this information. Another part of the voltage. Regarding voltage, we know voltage is the if it is unbalanced scenario, like phase A has the current or voltage now only, right? That means we have unbalanced scenario now. We don't have same information for all the phase. Only VA has the information of voltage over that fault impedance ZF. Okay. So VA will be unbalanced voltage, and that can be resolved to its equivalent 0, 1, 2 domain. Okay. So 0, 1, 2 domain will give us the information of impedance. Actually, VA can be written like in terms of EA. How can it be written? If you can recall the last class, like VA0, VA1 and VA2. What is the information of VA0, VA1 and VA2? This thing. VA0, VA1 and VA2. Okay. This information is derived from the sequence network generator, three-phase Y generator. Okay. That information, the outcome of that execution will be there as VA0, VA1 and VA2. That was discussed in last class before the single line to ground fault. If you can recall, only if you can recall, the positive sequence will have the source voltage or internal EMF voltage, right? The other two will not have any voltage source.
Yes, sir.
Now that equation is used now for different scenario of single line to ground or double line to ground. That means VA can be VA0,
Sir, why the
VA1,
other two
VA2.
don't have any voltage source? I couldn't understand that part.
Which one? Why the other two?
Two
Other,
don't.
yes.
Yes, sir.
VA, that means only you have positive sequence impedance will have the information. The other will not have any information for internal EMF. Okay, because the generated EMF was balance, there is only positive sequence voltage. Okay. And one thing I have to mention, up to now, what you have calculated or for three-phase system is only for the positive sequence calculation. Okay. The calculation or the circuit solution in terms of AC, which you have done in second semester or up to now, that is only considering the positive sequence scenario. Okay, positive sequence scenario will have the source voltage, and your calculation, if you just want to specify or want to make concise response, that solution is only for positive sequence solution. But you have not solved the negative or zero sequence. So if you are asked to solve the circuit in terms of AC, that is actually only for positive sequence solution. But from now on, you have to include the other two, which is zero and negative sequence, without having the source information.
Yes, sir.
Actually, that thing, what we have discussed, it's actually theoretical part. So it will be better if we can address that in terms of mathematical solution, so that you can have the numerical concept, what is going on in terms of response, in terms of numerical response. Okay. And the steps regarding these types of problem, you have to address the current determination. After derivation, you will have some current information. Okay, IA0 and IA. This is the fault current you have to address for all the case. It might be fault current. This expression will be different for different fault. Okay, IA. This derivation outcome you have to remember. Or what is the fault current for single line to ground? What is the fault current for a double lines case? That is the fault current. IB is minus IC in terms of A operator, and IB will have the value if you put the information of A operator. And this part, this thing, IA1, this part is also important. How they are related, Z1, Z2, and ZF. If you can recall, last class we have also 3ZN, single line to ground for. This one is there, 3ZF for single line to ground for derivation in terms of IA0. Okay.
So we did not finish it, sir. This one.
Which one?
The single
one.
line to ground, sir, we did not finish it, sir.
Single line to ground fault was covered, but you have not started other
And one single line to ground, we finished it up to this part, sir.
This
Equation
part, right?
1060, 10.60. So
60, this part. Okay.
Yes, sir.
If up to this point, it's actually covered. VA can be put like this equation. We have covered that part actually, and I have shown this diagram as well. The equivalent circuit, if you can recall how they are interconnected. Yes. Yes.
So sorry. For the single line to ground fault, the fault current is IC. I thought IC was zero.
I
thought IC was zero.
Which one is zero?
IC and IB for single line.
Single line IB and IC is zero, right?
Yes,
IB
but the fault current was IC.
For fault current is IA.
Oh, IA.
Not
okay.
IC. IA. Only IA.
IA. Okay.
Only IA. So fault current equation is derived from based on this formula, and that formula is in terms of this circuit, equivalent circuit. Actually, how it was derived, this voltage can be represented in terms of fault impedance. Okay. Is this part clear? How it is coming?
Yes.
10.61. Voltage can be replaced by ZF and IA. This is all there. ZF IA, right? VA voltage across phase A. This is the voltage across phase A, right? And we can get the drop of IA, but IA has the relation in terms of IA naught, right? From this, IA will have the relation of IA naught, so that will be 3 IA naught. And from that, we can get VA equals ZF IA, which is 3 IA naught, right? So this part is there already. So when we get the simplification, we can extract the IA0 part in terms of voltage, internal voltage, which is positive sequence internal voltage, and the impedance Z1, Z2, Z0, and ZF. Actually, this part you have to be careful how this equation generates the equivalent circuit. Can you have the idea how this is drawing based on this equation? Actually, here you can see all the impedance are connected in series, right? Z1, Z2, Z0. So Z1 circuit, Z2 circuit, and Z3 circuit should be connected in series. Okay. And also 3ZF. 3ZF is through this path. So they are in series, and you will have the current IA naught. This current IA naught will be EA source is there. So this equation can be drawn in the circuit like this orientation. Now, if we just want to check the other fault, in that case, what will be the circuit behavior or equivalent circuit response? This is the circuit response of uh, double line fault. Here you can see this part is absent, right? The third part, only positive sequence part and negative sequence part is there for double line fault scenario. And this part is not there. And how they are connected? They are connected in which configuration? Parallel.
Isn't it series, sir?
Oh, sorry, it is in series, right? Series, because these are connected in series. But if it is there, it will be parallel. Okay, in that case, third line, the third scenario, double line to ground, that we can see also what will be the behavior of double line to ground. Actually, there will be some equation after derivation, some kind of equation will be there, and that equation will give you the indication of this circuit. Actually, here you can see how they are connected. ZF, Z0, Z2, Z1, 3 impedances are there, but the circuit configuration is for double line to ground fault. That is not similar to single line or double line scenario. It is the double line to ground fault equivalent circuit. So actually, we want to see one practical problem so that it will be more feasible or under view. Regarding those issues, when we want to solve this type of problem, some tabular information will be given. Okay, these types of tabular information will be there, and what to do or which information you have to extract from that tabular information. Like how many elements are there in that configuration? 2 generator, 2 transformer, and 3 line. Okay. And here you can see in the table X1, X2, and X0. So from this information, you can understand X1 and X2 information. You can check those information table or column. They are same, right? But you can get different information for zero sequence reactance or zero sequence information. Can you check there? They are different, right? Only positive and negative sequence reactance are same, but zero sequence informations are different. Now, what we have to do, the single line information is given and generator is grounded through current limiting reactor, which has the value of some information 0.25/3 per unit on some base 100 MVA. The information are given in tabular information. Okay. Determine the fault current for the following faults. Actually, some information like this, you have to determine three-phase fault, which is the symmetrical fault. Then you have to find single line to ground fault at bus 3. Regarding that, bus location is important. Which bus you want to find the fault? Double line to fault for bus 3 as well as double line to ground fault. That means you have 4 different scenario to address the fault current. And for that, you have fault impedance of 0.1. Okay. So have you got the problem and what you have to determine? Regarding that fault or that problem, how can we address that scenario? This is the diagram, single line diagram, where how it is connected to generator, to transformer, and three line. So this is nothing but single line diagram, right?
Yes, sir.
And in single line diagram, if you can recall, there will have some information regarding the internal connection of generator and transformer. One important aspect regarding this fault calculation is the transformer equivalent circuit or zero sequence network. That will be different because transformer will have different configuration possibility. Right? Be Y, it might be delta, it might be solidly ground or not. So let's see different feasibility or different possibility or transformer configuration. And for that transformer configuration, equivalent circuit for zero sequence circuit, here, this is the transformer different configuration. The first possibility, the transformer may have Y configuration, right? That Y may be grounded, that Y may not be grounded. First one, both the side, primary and secondary will have ground connection. But second case, you have only primary ground, secondary open. Third configuration, primary Y ground, secondary delta. Okay. Fourth configuration, you will not have ground for Y and delta. So zero sequence circuit based on this different configuration will be given here in this chart or information. Actually, how to replace that zero sequence transformer circuit to generate zero sequence equivalent network, because you have generator, you have transformer, as well as you have line. For line, you can replace easily by equivalent reactance information. For transformer, you have to use proper zero sequence circuit based on internal configuration in terms of primary and secondary. Okay. Now let's move back to our original scenario. Remember that they are different. This is for zero sequence circuit in terms of YY grounded. And here you can see if it is not grounded, here you have some open path, right? Which part it is open? In primary or secondary? This opening connection or open path?
Sir,
Primary.
it is in primary, sir.
Why?
No, sir.
Here you can see the equivalent, actually the transformer symbol. Which part has ground? Primary
Secondary.
or secondary?
Secondary.
Secondary has open, right? So secondary open, that means this path is secondary side, which should be open. Okay. And if it is Y delta, in that case, the configuration will be something like this. That means zero sequence transformer equivalent circuit. And for Y delta, you will have the configuration like this. So you might have delta delta as well. Delta delta, you have to replace your circuit of transformer in terms of this diagram. That means when you want to draw the zero sequence equivalent circuit in terms of transformer delta delta, you have to use this configuration. Now move back to our original problem where we have started the journey. The different configuration for transformer zero sequence circuit. Yeah. Here we have started the journey, right? Here you can see the transformer T1 has both ground, right? But transformer T2 will have delta and Y. So you have to draw accordingly the zero sequence circuit. First of all, you have to draw positive sequence circuit of this single line diagram. How can you draw that? You have to replace all the information to its equivalent. Which information you have to put as reactance? You can put the reactance equivalent of the generator, right? Generator 1 is reactance equivalent, but reactance information, you have three reactance information for generator. Here you can see generator 1 will have x1 as well as x2 as well as x0. Okay. So when you want to draw the equivalent circuit for sequence component in terms of positive sequence circuit, you have to use this information or this column information. Okay, remember that. Here you can see all the information regarding what is the generator 1 x1.15, right? Generator 2.15 as well. Transformer 0.1.1. Line 125, 1525. 125, 1525, and this is the connection for positive sequence impedance only. So addressing this type of problem, what you have to do, you have to draw all the sequence component individually. First step, you have to replace all the impedance information in terms of only positive sequence information. So when we replace this symbolic diagram or single line diagram or one line diagram to its equivalent reactance information or impedance information, this diagram will be known as now positive sequence impedance diagram. Okay, this information, this diagram. Earlier you can address only impedance diagram, but now you have to mention specifically that this is positive sequence impedance diagram. So positive sequence impedance diagram, after rearrangement, this delta part can be replaced to its equivalent Y, delta Y configuration. We know how to shift delta Y, right? Can we do that? Delta Y shift for the
Yes, sir.
if we just want to find this part, this simple part, how can we find that? Multiplying these two and divide by the summation of all the three to get this information. Okay, try to check that whether you can get that or not. This first part, multiplying these two and divide by all the three summation. Only one part you can make the calculation so that you can understand that, the first part, and repeat that process for the other two also. Have you got that?
So once
Have
more,
you-
so once more.
Have you got the equivalent Y branch? Y part of this? That means using this to convert this delta to its equivalent Y. This information, can you find that? By multiplying these two, divide that by all the three to generate this information. Whether you can get that or not.
Sir, multiply the 2 and divide it by
All the three.
All the three summation. All the three summation.
sums. Okay.
So are you
That's
converting the diagram into
matches.
a delta to y?
Delta to y, right?
Yeah.
To get the equivalence impedance for the total network. Okay, that's the main target or objective
Yeah.
to do that. Our objective is to generate the equivalent impedance in terms of bus 3. Bus 3 is the fault bus now. It is mentioned in the bus 3 has fault in terms of fault impedance ZF 0.1. So we want to find the equivalent circuit in terms of bus 3. For that case, we have shifted our delta circuit to its equivalent Y so that we can use this as series and this one series with parallel to this part series. After resultant solution, we can get Z1s, Z2s. These are Z1s, Z2s, and Z3s by delta Y configuration. Okay, delta Y configuration will give us, this is the ultimate Z331. Regarding that notation, Z331 means you have fault bus as 3. Okay. If it is fault bus as 2, you have to use Z221. Okay,
Sir,
Z33, yes.
how does it get those values
Which
here?
one? Which one? Yes,
Z331,
what's
yes,
your
these values. Yeah.
yes, Z331 is generated based on parallel configuration. Actually,
Oh,
Z331 is the fault impedance, equivalent impedance in terms of bus 3. Okay,
okay.
or Thevenin impedance, you can say. Thevenin impedance across the terminal bus 3. Bus 3 will have, this is the bus 3, and for that, you have to add these two. That means this part will be added and this part will be added, and they are parallel, right?
Yes.
And these are in series with that parallel response. This is Z331,
Oh, okay.
the total Z331. These are added and these are parallel. This parallel will be added to this part series.
Yes. Yes,
So
understood.
Z331 is now in our hand, which is 0.22. Okay. So this is actually what? Thevenin equivalent impedance for positive sequence
Sequence.
impedance, positive sequence network, right? Positive sequence network will have the source, and we can use the same information for negative sequence circuit as well. Only source will not be there. This is the difference. Okay.
So that's the
Z1
only difference, right? So
can be equivalent. Only source is not there for negative, but the
okay.
information value is same for Z1 and Z2. The impedance information value. Okay. Because why it is same? It is from the chart. You can see there it is not difference, right? X1 information and X2 information, they are same. So when you draw the same procedure, you will get the same result. But when you
So
want to
are they
adjust the
always the same?
other part, they will be always same, X1
Okay.
and X2. But try to check whether there is any anomaly or not. Generally, it will be same, X1 and X2. But if it is difference, in that case, it will be exceptional, or you have to check when you start the problem solution, whether it is same or not. If it is same, you can use the Z1 information to third one, Z0. Z0, regarding Z0, you have to be careful. They are different, right? This column is different than the other two. So now you have to do the same Thevenin equivalent resultant for Z0 as well. And another important consideration regarding the transformer part, when you want to put this information, transformer 1 and 2, you have to be careful about the equivalent circuit for zero sequence network. Okay. Zero sequence transformer network, you have to draw according to the connection of transformer primary and secondary. For this case, transformer T1 and T2 are different, right? Internal connection. So you have to draw the connection when you want to draw the equivalent circuit. Let's see what we have done here. Here you can see there is open terminal, right?
Yes.
Why it is open terminal? This part is same. But here you can see the difference. This is open terminal because T2 transformer has delta there. And delta in this part, that means upper terminal. Okay, let's check there. The delta configuration for T2 is in the upper terminal. So you have to make open that delta. So
Sir, can you repeat this, sir? Why is it open, sir?
open regarding, okay. Be careful about zero sequence network diagram configuration, especially for transformer part. Okay, when we want to put the equivalent information for all the generator transformer, here you can have transformer 1, transformer 2. Okay. Regarding transformer 2, here you have some open terminal because of delta in the upper part. Lower part is the Y and upper part is delta. And I have already shown the equivalent circuit for transformer internal configuration for Y delta.
Okay, sir, I understand, sir. Okay, okay. Sir.
Y delta position will give you indication whether it should open or not. So based on that, and it is applicable for only zero sequence circuit, not for positive, not for negative, only for zero sequence circuit. Okay, you have to be careful about that. If it is has any delta, you have to draw the circuit accordingly based on the zero sequence transformer equivalent circuit. So when you have drawn this configuration like the earlier one, now you can put the information. Actually, you can find the equivalent Thevenin equivalent impedance across bus 3. And how can you do that? When you make the calculation, you have to consider this path, that delta, inner delta, right? 2 is equivalent Y. Then this part, regarding that part, that is actually not required for zero sequence circuit. Is it there in the connection? This connection is completed through that ground, right? So you have to consider up to this point. This part will be cancelled, or this part is not required for the equivalent circuit or equivalent impedance calculation. So after calculation, you can get the equisequence impedance as 0.35. Is it clear? Because this is very
Yes, sir.
important.
মোটামুটি, sir, yes.
মোটামুটি হলে হবে না, পুরোপুরি ক্লিয়ার হতে হবে।
মোটামুটি,
If
sir.
the confusionের জায়গা, you can address your confusion. Which part you have the
The
confusion?
problem is, sir, I'm confused about what I'm confused about, sir. It's
Acha,
a
okay.
loop, sir. It's a loop, sir. Yes, sir. I have to give it some time.
Regarding
Sir.
that, actually, okay. Okay, let me clarify simply that what you are doing. First
Yes, sir.
step is
Yes.
to consider the equivalent impedance for all the sequence component. Okay, that means Z1, Z2 as well as Z0. If you have been given any circuit, any single line diagram, what you have to do? You have to put the information for different scenario. This is the single line diagram, might be another single line diagram. Okay, this is the first step to address these types of problem. First step is to generate the equivalent impedance for all the sequence in terms of Thevenin concept. As the bus fault occurs at bus 3, you have to find the equivalent impedance considering bus 3. It might be other bus as well. It might be 1 or bus 2 as well. Second step, when you complete all the Z calculation, Z1, Z2 as well as Z0, then you can proceed for fault current calculation. Okay, because now you have all the Z in your hand, you can address fault calculation based on different scenario. It might be balanced three-phase fault. For that, I3A will be V30 over Z33 and ZF. Here you can see Z331. This is the how can you interpret that notation? This is for fault bus at 3 in terms of positive sequence component, right? And also fault impedance is there. Sometimes regarding that fault impedance ZF, it might be mentioned that bolted fault. Okay, bolted fault indicates ZF as 0. But for this case, as ZF has value, it is not bolted fault. It is mentioned in the problem identification, the earlier part, ZF has 0.1. But if it is ZF is not 0.1, it might be bolted fault case sometimes. That means you don't have any fault impedance for that fault path. In that case, you have to put this part, the second part of that equation for balanced three-phase fault calculation as 0. Okay. So the upper terminal, the voltage EMF, the voltage EMF should be considered in terms of 1 per unit. The fault current will be I3A. Okay, I3A will be, it is in terms of fault scenario that can be calculated based on V30, which is 1. V3, it might be V3 other phase also. Because we have fault at phase A, we have considered that scenario, and that will have the indication of fault current. Then second scenario, the single line to ground fault at bus 3, the derivation response. This is the derivation result, right? I30, I31 and I32. If you can recall, this is the IA0. IA0 and IA0 will be I3, only you have single line to ground for this part, right? IA0 and this is I30, this I3 information in terms of phase A. Okay, so here you can have I3B and I3C. I3B and I3C is 0 due to single line to ground fault. Only I3A will be there, which is I30, 3 I30, right? And when you put this information after matrix multiplication, you can get that. Actually, these types of problem you have to practice by yourself. Otherwise, by observing, you cannot understand the total picture. I will share this content to you. That is covered from Hadisadat book. Now, earlier topics was covered from Stevenson Granger. It is covered from Hadisadat topics. So, fault current calculation for different scenario. Let me give a brief idea or brief overview so that you can get some clue what are the important steps regarding solution. First step is to generate the fault current in terms of ABC sequence, I3A, I3B, I3C. This is I30, I3A, I3B, I3012. I3012 is there. So single line to ground fault besides line to line fault, the steps will be I31 and I32 because of third phase volt scenario for I31 and I32. The negative and positive sequence will be same, but I30 will be 0. This is for double line to ground fault. Sorry, line to line fault. Double line to ground fault, it will be complex. This one. This is the complex expression for I31 and I32 and I30. And for single line to line fault, you will have this negative sign information for current calculation. For current calculation, first step is to determine fault current for all the scenario. And when you complete this fault current, you have this part as 0, 1, 2, and this side is ABC in terms of I3. So after completion, you can get the total fault current for double line, which is I3B plus I3C. This part is for double line to ground fault. For other fault, you can use only IA information. You can check here for fault current for line to line case. It is same for both the phase. I3B and I3C is there in terms of negative polarity. I3A will be 0 for the line to line. For fault current in terms of single line to ground, you will have only phase A information, which is I3A, I3B and I3C. I3C will be 0. But for double line to ground case, you have IA 0, IB 0, I3 0, and I3. This is 0, 1, 2. I3 1 and I3 2 is there, and you have to use that information to generate the total fault current. For double line to ground fault, you have to make addition after the calculation. That means when you complete that calculation, you have to use these two information to get the final fault current, which is only for double line to ground fault. Okay, remember that double line to ground fault. After solution, you have to use the final outcome. This one. Actually, this problem requires two-step solution. First step is to generate the Thevenin equivalent impedance to address different Z. Second step is to determine all the fault current in terms of different configuration. That's the final or total picture of this problem. So if you have been given any single line diagram, what you have to do, first step is to consider all the impedance in terms of Thevenin circuit concept to get the resultant impedance. And when you want to generate the resultant impedance, that resultant impedance should be all the sequence impedance, positive sequence impedance, negative sequence impedance, and zero sequence impedance as well. Okay. So when you have all the sequence impedance Z0, Z1, Z2 in your hand, you have to use those three sequence impedance for fault current IA determination based on different scenario, like single line to ground fault, double line to ground fault, line to line fault, and three-phase fault. These four observations can be possible if you have generated the impedance information correctly, Z0, Z1, and Z2. So that's all for today, the topics discussion. If you can recap the idea, what are the different fault scenario, fault scenario for expression like this, Z1, Z2, ZF, IA equation. It can be different for other scenario, like single line case, it is IA expression will be IA Z1, Z2, Z3 as well as ZF. Z0 will be there, but for line to line fault it is not. And based on this circuit equation, you can draw this equivalent circuit from that equation, and they are different for different scenario. So here it is mentioned the bolted fault case ZF should be 0. In some case it might be mentioned bolted fault as ZF 0. Okay, but for this scenario, that means the problem, it is mentioned ZF has the value of 0.1 per unit. So when you solve this problem, you will get the total picture of this course in terms of regular solution. That problem solution can be done based on other approach by ZBus building algorithm as well. Okay, that means your ZBus information will be given to you, and from that you can find the same solution for determination of fault current, bus voltage, and line current. These three information. So fault current can be determined by two way, like ZBus. You can determine by two way, right? One by inspection, another one by bus building algorithm. Fault current can be also determined by two way, like normal Thevenin equivalent concept or ZBus building algorithm concept. Okay. So today we have discussed regarding Thevenin equivalent concept for determination of fault current using four different case for fault. You will be given some tabular information in terms of positive, negative, and zero sequence, and you have to use, or you have to collect this data to generate your Z1, Z2, or Z0, which is applicable for fault current calculation. So can anyone review the discussion, or in short, what you have understand from this class, so that I can make a correction based on that observation?
Could you kindly
Tasin, what are the summary? Can you summarize in 2 lines what we have to do? First of all, if this is the scenario, or if you have been given any single line diagram, can you address the fault current?
Manas sir, yes, we have to just start with Thevenin.
what
First,
will
we have to
be
find the
the-
Z equivalence using the Thevenin
Z
theorem.
equivalence for 3 different scenario. Okay, that
Yes,
means
sir.
Z0, Z1, Z2.
Yes, sir.
And when
Yes,
you
sir.
use Z0, be careful about transformer zero sequence circuit. First step. Second
Yes, sir.
step, when you find all the Z, you have to use those Z for fault current in different scenario. It might be
Yes,
for
sir.
all the fault, or you might have single fault.
Yes, sir.
That means
Yes.
only one fault will be addressed. In this case, if it is already mentioned, or it is given for all the fault. So how can you address, or how can you generate the Z determination? When you want to determine Z, you have to use this table. Okay, this tabular information.
Okay, sir.
And
Yes,
how
sir.
can you put this table information? By replacing all the symbolic information like generator, transformer. What is the generator information for X1 0.15, right? And
Yes, sir.
transformer 0.1. So check 0.15 and 0.1 there, right? For this path. For second path, it is generator 2, transformer 2. Here you can see the difference. The positive sequence transformer equivalent circuit, it will not have any impact to the internal configuration. Okay, remember that. Only zero sequence transformer equivalent circuit has the internal circuit issue.
Okay, sir. Okay.
This part you can see, this is the simple single line diagram, right? But
Yes,
if
sir.
it is for regular or positive sequence. So what you have solved on three-phase concept. That is, you can precisely say that is applicable for positive sequence calculation only. Okay.
Yes.
And if you are like the earlier scenario that when you want to solve the impedance matrix determination, that is positive sequence impedance matrix only. So it
Okay.
impedance network was there, but if you specify that, it will be only positive sequence impedance. So you can easily draw positive sequence impedance without considering the transformer internal scenario. But when you want to address transformer zero sequence circuit like this one, for this case, the transformer internal circuit in this part, it is delta is there, and this
Yes.
you have to consider. So zero sequence transformer equivalent circuit, you have to be very careful.
Yes.
So that's all for today.
Why don't we do the negative sequencer? Why don't we do that?
Negative sequence you have, but it is same. Z1, Z2, this is negative sequence. Negative sequence
Okay.
network is there, but we have not made that similar calculation because these values are same for positive and negative. We have just put that information equivalent. Here you can see the positive sequence reactance, negative sequence reactance is there, right?
Okay. Okay.
Only the difference, value is same. Only the difference is the source issue. In that positive sequence network, you have source with the value.
Yes.
Negative sequence network without the source. This is
In the
the
zero sequencer, do we have a source?
zero sequence does not have source.
Exactly.
But it has value difference.
Yes. Has it.
It will not also have source.
Yes.
Only positive sequence has the source. Okay.
Yes.
The other sequence will not have any source. They are the derived outcome. They are not the source. So if we just think of the regular scenario, it is positive sequence circuit. So
Yes.
if you just say a three-phase circuit solution, is better to mention positive sequence three-phase circuit you have solved up to now. You have not deal with the negative sequence or zero sequence. From now on, you have to consider those issues as well. The zero sequence scenario, what you have to consider in terms of transformer circuit. If it is regular, in that case, you don't need to bother about this configuration. But as it is zero sequence, you have to think of it.
Yes, sir, I understand.
Sir.
Little bit, right. And now you can understand. Actually, when you solve this problem by your hand, I will
Yes.
provide that content. You will get
Yes.
the total picture more.
Inshallah.
Sir,
Yes.
sir, please, how will you know it is a zero sequence?
Yes. Is there any question?
Sir, I mean, how will you know that it is a zero sequence?
You have zero sequence, you have to determine. You will not know. You will be given only the single line diagram.
Okay.
This single line diagram will be given to you.
Okay.
You have to generate that.
Okay.
Based on tabular data. This tabular data you have to put in the single line diagram to generate different sequence impedance. Z1, Z2, and Z0 based on those information.
Yes.
And regarding drawing of transformer, especially careful about zero sequence transformer circuit drawing, equivalent drawing. This is the single line diagram, and the lower part is the equivalent, the impedance diagram, right?
Yes.
And it is positive sequence impedance. So positive sequence and zero sequence impedance will have only difference in terms of transformer connection diagram, and the value will be different for both the case. Because the tabular information is different. For positive, it is 0.15, right? And here it is 0.5 only, 0.05. Another thing, current limiting reactor is connected to neutral of each generator grounded through per unit base. This is you have to consider 0.5, 0.05, 0.25 or zero sequence 0.25. Here you can see 0.25 as zero sequence consideration. So this thing you have to careful. That means when you want to draw a zero sequence circuit, You have to be very careful. Regular drawing is positive sequence circuit, but zero sequence circuit, you need to be careful. And when you have all the Z as well as ZF, you can find the fault current for different scenario. So thank you all for attending today's session. This is from 10.5 from Hadis Sadat book. I will give that document, but if you have the content, you can check that content 10.5 from Hadis Sadat book. Thank you all for attending today's session. I may conclude today's session if you don't have any question.
No questions. So thank you, sir.
Thank you.